Hello and welcome to another video on basic fiber optics. Today I'm going to explain the nonlinear Schrödinger equation and how it can be solved numerically using the spin-step Fourier method in order to simulate optical pulses propagating through an optical fiber. So first I'll explain the theory behind this equation, and then I'm going to show you an implementation, a numerical solution to this equation implemented in Python, which you can also download and play around with. So let's get started. First of all, what are you trying to simulate here? Well, we want to simulate the propagation of an optical pulse through an optical fiber, which means that we have the field in its envelope at the input of the fiber. We want the field in the envelope at the output of the fiber. We're going to assume we have a pulse with a certain overall duration, t0, centered at some carrier frequency omega naught, where the overall duration of the pulse is much greater than the duration of a single optical cycle inside of the pulse here. What are some of the physical effects you might want to consider inside an optical fiber? Well, we have attenuation, group velocity dispersion, self-phase modulation as some pretty significant ones. There's of course also other effects, but let's just focus on these three here just for simplicity. So attenuation is fairly simple to understand. It just causes the power of the pulse to exponentially decrease as we propagate forward. Group velocity dispersion arises because the refractive index of the glass inside of the fiber depends on the frequency of the light propagating within. So if you have a pulse with a finite duration, it's going to have some kind of spectral width with different spectral components, and if their propagation speed depends on the color, then certain colors will propagate faster than others, which will generally cause the pulse to broaden out and also obtain a chirp so that the frequency actually changes over the duration of the pulse. Self-phase modulation is a nonlinear effect, which causes the refractive index to be locally increased, where the intensity of the pulse is very high. For example, the peak part of the pulse here will experience a higher refractive index than the initial part right here, simply because the high power effect causes the glass to compress a little bit, at least optically, or more dense. This also means that the refractive index, and therefore the phase shift that the pulse experience, changes over its duration because the power changes over its duration. That actually modifies the frequency of the pulse and causes it to broaden in the spectral domain. In order to model all of these effects, we need what's called nonlinear Schrödinger equation, and it's also how the envelope changes based on the attenuation, the group velocity dispersion, and the self-phase modulation. Now, this is kind of a tricky equation, as you can probably see, so let's try and look at these individual terms in isolation without considering the other ones, in order to get a better feel for how they operate. So as mentioned, attenuation is fairly easy to understand. It just causes the pulse power to exponentially decrease as we propagate forward. Note that alpha over 2 changes the amplitude of the pulse, whereas alpha changes the power of the pulse. So just be aware that if you're reading sources on fiber optics, some authors use alpha as the field attenuation coefficient. Some people say alpha is the power attenuation coefficient. So just be aware of that distinction when you're investigating this for yourself. Now, group velocity dispersion. If we imagine we have a very short pulse going into the fiber spool and we ignore all the other terms of the nonlinear Schrödinger equation, we basically get something that looks identical to the heat equation. Essentially, this can be solved by computing the Fourier transform on both sides of this equality here, and then applying this complex exponential, and then take the inverse Fourier transform to go back to the time domain. The idea is that all of the different frequencies will get different phase shifts, and that actually causes the pulse to effectively broaden out. Now, note that beta 2 greater than 0 is referred to as normal dispersion. In this case, red light will propagate faster than blue light, which leads to a negative leading chirp here, because the front part of the pulse becomes more red because the red light is sort of shifting forward, while the back part becomes blue because the blue light is trailing backwards. And conversely, if beta 2 is smaller than 0, we refer to this as being a normalist dispersion, in which case the blue light will pull ahead and the red light will trail behind. Now, self-phase modulation is a pretty interesting effect because actually it doesn't modify the overall shape of the pulse. The envelope actually stays constant, but it does change the underlying phase of the pulse and actually modifies it. According to this complex exponential here, where gamma is a nonlinearity parameter, it is of course the length of the fiber, and this is the power of the pulse, which of course is computed from the absolute square of the envelope. So the envelope stays the same, but actually the spectrum is broadened, as we'll see in a moment. Note that the gamma is pretty much always greater than 0, which leads to a negative chirp in front, so red shift here, and a blue shift in the back. Now, in the spectral domain, initially we'll be launching in just a sort of very clean spectrum like this, just a sort of Gaussian spectrum shape with a certain spectral width. But as it propagates through the optical fiber, self-phase modulation will cause power to be transferred from this main optical frequency into a whole range of other frequencies out here. So just to be very clear, group velocity dispersion only takes some of the pre-existing frequency components and then delays or advances them relative to each other. But cell-phase modulation actually creates new frequency components by transfer of optical power. That's one of the reasons why we find optical or nonlinear effects in optical fiber so interesting, because they allow us to generate more colors from just a monochromatic input. I actually have a video that should be linked up here where I demonstrate this experimentally, so feel free to check that out. Anyway, how do we actually solve this very complicated equation here? Because it contains a derivative in the z direction, there's a scaling factor, then a second derivative in the time, and then it has a scaling factor that somehow depends on the absolute square of the thing we're trying to model in the first place. So clearly this is kind of a tricky equation. We could use an ODE solver to compute the solution, but there actually is a faster way we can do it. An observation we can make is that it's very easy to apply the effect of group velocity dispersion as well as loss inside of the spectral domain, because all we need to do is multiply by a complex exponential, like so. Whereas it's also very easy to apply the effect of cell-phase modulation in the time domain, because we just need to apply this complex exponential right here in order to compute the effect of shifting the pulse forward by dz. However, computing this effect here in the time domain requires us to take that second derivative in the time, whereas computing this one in the spectral domain will require us to do a convolution, which is kind of an expensive or complicated operation. So maybe we can get away with simply applying the effect of dispersion and loss inside of the spectral domain, then shifting to the time domain and applying the cell-phase modulation here, then switching back again. That's essentially the idea behind the split-step method. We start with the envelope of the pulse at some certain location set inside of the fiber. Then in order to push it forward by delta z, we first apply the effect of cell-phase modulation. Then we compute the Fourier transform in order to go to the spectral domain. We apply the effect of dispersion and loss. Then we compute the inverse Fourier transform in order to switch back to the time domain. And then we just keep looping like this until we reach the end of the fiber. So with that strategy in mind, let's take a look at a Python notebook I wrote in order to actually model this simulation here numerically. So stay tuned for that. Alright, welcome to this Python notebook I wrote from scratch in order to simulate the split-step method and solve the nonlinear Schrödinger equation numerically. So this notebook here only considers sort of a scalar implementation of the nonlinear Schrödinger equation. It could in principle be upgraded with to also take sort of polarization, that is vector components, into account. It's a bunch more upgrades and like tweaks you could make to it. But for now it just simulates the effect of loss, dispersion, and nonlinearity. So there should be a gamma here with a let's just fix this just to a little bit. Just think about that. Alright, that should make it better. Right, sorry about the interruption. Anyway, the point is that this notebook is actually available online through this link here. It's going to be in the description, of course, and it'll also be available on my GitHub page right here if you're interested. Along with a very, very bad version of the code I wrote for my thesis, but that's neither here nor there. Anyway, let's actually get started. So the first thing we want to do is import some useful libraries. Of course, we have NumPy, SciPy, FFT functions. So both the Fourier transform and the inverse Fourier transform, as well as some other functions we'll need here. We have matplotlib, and of course we have pi being defined globally. So the next step we want to do is define the number of points we want to define our time axis with. So the idea is that we want to simulate this numerically, so of course we need a time axis with a certain number of points and a certain resolution. In this case I've chosen 100 femtoseconds as the time base. Now we're going to define also the frequency axis, because of course when we take the time axis and convert to the spectral domain, we're going to need something as a base to plot our Fourier transform. So first we just generate the time base right here, and then you could be tempted to just use the FFT frec function from SciPy, and in that case you're going to get a frequency list I call fbat, and you'll see why in a moment. Alternatively, you can use both FFT frec and then the FFT shift function. Just to see what's going on here, if you just use the FFT frec function directly, it provides you with a list of frequencies that begins with all of the positive frequencies and then jumps to all the negative ones afterwards. Now, I have no idea why SciPy was programmed in this way. It seems kind of inconvenient, but for some reason that's how it's designed. So in order to make sure that you properly arrange everything, all the contents of this list, you have to use the FFT shift in order to shift all the negative entries to the beginning and all the positive entries to the front. Now, you have to be aware of this, because when you apply the Fourier transform and the inverse Fourier transform, SciPy expects this kind of weird sort of cut-up layout here for some of those operations. So just be aware of that when you try and play around with it for yourself. Anyway, I've also defined a class here that holds the simulation parameters. Of course, this work now because I forgot to run this one up here. So let me just get that. There we go. Okay, so the point is that I've created a class here that contains all the information about the simulation that we're interested in. So you simply feed it the number of points you're interested in and the time step, then it generates and saves the time list as well as the frequency base we're interested in. And also wrote a little self-described function here that just prints out some of the configurations here in a bit more of a readable format. Alright, we want to simulate some Gaussian pulses propagating down the fiber. So first we need a function that computes the power of that pulse given the amplitude by simply calculating the absolute square. We can also find the energy by simply integrating the power from before with respect to time. Luckily, this also works in the frequency domain. If we give the spectral amplitude integrated with respect to frequency, we also get the energy of the pulse. And here we simply have a simple Gaussian function that will spit out a Gaussian pulse here. Note I'm multiplying by 1 plus 0j in order to make sure the output is complex. That's because we want the bit amplitude to actually have a phase, so this is just a way to ensure that all the things we calculate are complex from the beginning, so we don't run into sort of unit conversion problems later. I guess more like type definition problems. Anyway, let's actually take a look at this Gaussian pulse here. So if we run it, we just get a nice Gaussian shape out here with a certain duration of around, it's like a width of like 20 picoseconds or something. Okay. We also need a function for actually converting from the time domain to the spectral domain. So for that, we have a function called getSpectrum from pulse. You feed it a time basis and the pulse amplitude. Then it first calculates the pulse energy, which we'll save for later. Then the frequency axis, and then the dt time step here. Then we simply take the Fourier transform and then the FFT shift in order to avoid that weird sort of cutting behavior. We also multiply by dt in order to keep all the units consistent. Then we compute the spectrum energy, and then we compare the pulse energy from the start to the computed spectrum energy. The reason why we do this is that it's sort of a little sanity check, because when you compute the Fourier transform, it shouldn't change the energy of the thing you're modeling. It should be conserved. So this is just nice way of catching any kind of funky errors going on. And of course, we can also say go the other way. We can define a function that gets the time basis from the frequency basis, then a function that gets the pulse from the spectrum in exactly the same way with the same kind of error check right here. And also a function for generating a Gaussian spectrum given a frequency basis and amplitude or bandwidth that you might be interested in. Right now, it doesn't support different carrier frequencies, but that's something you might want to implement on your own. Okay, so let's just check the percent functions here and see if it works. Yeah, and we see that the Fourier transform of the test pulse is the same as just generating a spectrum using the Gaussian spectrum function here. Right, so now we've sort of set up the input time domain, but we also need to discretize the fiber that we're going to propagate the pulse through. In order to do that, I've created a class just called fiberConfig, which takes in the number of steps we divide the fiber into, its length, its gamma value, its beta 2 value, as well as its loss coefficient. So note that if we divide the fiber into, let's say it's 2 segments, 1 segment, we actually get 2 calculated pulses out. We have the input pulse and the output pulse. And if we have, let's say, 2 divisions, then we get the input pulse, the middle pulse, and the last one. Just be aware that we actually care about both the number of steps we divide the fiber into, as well as the number of traces we're going to get out here. So anyway, using this information, we can sort of set up some of the important factors here, like the locations of each one of these calculated outputs, as well as the step size and so on and so forth. Note here that we're going to ask that the loss coefficient is fed in decibels per meter, but in here we actually convert to neighbors per meter. And the reason is that usually when we report powers, it's nice to use the log 10 scale, but when we do calculations, it's nicer to use the exponential. So that's why we use neighbors here. It's a pretty straightforward conversion from one to the other. Then here we can actually initialize the class with a certain length, a certain number of steps we want to divide it into, a gamma value, and a beta 2 value here. Note that that's typically reported in femtoseconds squared per meter. So here we multiply it by 10 to the negative third in order to convert that into seconds squared instead of femtoseconds squared. Also, the value of the attenuation is usually reported in decibels per kilometer. So here we just multiply by 10 to the negative 3 in order to get it in decibels per meter, so it's consistent with the length up here. Okay, so we initialize it here, and now we can actually define the split-step Fourier method function. So this one takes in a fiber configuration, a simulation configuration, and a pulse. So the first thing it does is to generate a pulse matrix and a spectrum matrix. These are used to store all the intermediate calculations computed all the way throughout the fiber. And then we pre-compute the dispersion and loss exponential, because that doesn't actually change in any of the steps. It's the same all the way throughout, so we can sort of pre-compute that to make it a bit more efficient. Then we can also compute the sort of scalar part of the nonlinearity. And then we simply just loop over all the steps we divided the fiber into. We multiply the pulse by the complex exponential to apply nonlinearity. Then we convert to the spectral domain and apply dispersion and loss. Then we convert back to the time domain Then we store the pulse in the spectrum inside the matrices, and then we just keep looping like this until we reach the end of the fiber, where we return the pulse matrix and the spectrum matrix. So now we can run it, and also store the input pulse and the input spectrum, as well as the final pulse and the final spectrum here. Now here I've defined a number of functions that simply just plot the interesting parts of these matrices. So it plots both the initial and final pulse spectrum, as well as the sort of 2D color plot of the matrices, and also a 3D color plot. So let's actually take off that. These guys, and we should get a nice output here. Yes. Okay, so here we see the initial pulse in blue as before, and we can see that the final pulse here has been attenuated a bit, also broadened because of dispersion, and I guess also the phase modulation increase in the frequency range, so it will drift more apart because of the dispersion factor. And here we see sort of the evolution of the pulse throughout the fiber in colorful 3D, normalized to the input peak power here. And here we see the pulse evolution, sort of seen from above. It's the same pulse here, but just from a bird's eye view. And we can do the same thing for the spectrum here, of course. As you can see, it sort of broadens out as we propagate down the fiber. Okay, so that's very colorful and interesting plots, but how are we actually certain that these physical effects have been modeled correctly? In order to verify that, we can do a little bit of unit testing. This means that we're going to test the effect of, let's say, loss, by both computing the effect by theoretical means, but then also by numerical means using the split step method. So here I'm defining a new fiber that only has loss with the same number of steps and same length, and then no gamma, no beta value, but the same loss value here. Theoretically, of course, I know that the final pulse should look like the input pulse multiplied by a negative exponential like so. And I can also calculate the output matrix here by simply using the split step method. So doing that, we should be able to compare the two results. Let's take a look. It should take a while to run. And there we go. So we see that the final pulse computed by the split step method and the initial one, or the final one computed by theoretical means, actually overlap completely. You can't even see the difference. And if you compute the difference numerically, you also see the discrepancy is very, very small. Now we can do the same thing for beta 2. So essentially we just compute the theoretical effect of beta 2 by using the heat equation, and then we also do it numerically. And then we can compare the two output pulses like so. You see that they definitely broadened a little bit, and also the theoretical result and the final pulse numerically are completely identical, down to a very, very small margin right here. You can also check the chirp has been generated correctly, because notice that beta 2 greater than 0 should lead to a negative front chirp. So here we just have a function for getting the phase of the pulse all the way across. Then the chirp simply takes the derivative of the pulse, or the derivative of the phase with respect to time, and then switches the sign here because of the way that the electric field is initially defined in this formalism here. But the point is that if we plot this, we see that again the theoretical result of the output pulse in terms of chirp matches the numerical computed one. So that's also very nice to know. And then for gamma, we can sort of do the same trick. We apply the theoretical result of phase modulation using this complex exponential right here, and then also using the split step method. Then we compare the outputs, and we should get something that's identical like so. And of course, we also check how it actually changes all the way throughout the fiber using these color plots here. So here maybe zoomed in a little bit too much, but you can see that generally the spectrum sort of broadens out here as we propagate down. Looks a bit like a butterfly maybe, not sure if this is visual here. And of course the discrepancy between the theoretical and numerical result is also very small here. And of course we also check the chirp here. We see that we indeed get a negative chirp in front and a positive chirp in the back as expected for a positive value of gamma. Okay, so as I mentioned before, I also did a practical experiment where I showed the effect of phase modulation. So I thought it might be interesting to sort of recreate that numerically. So I have a picture here of the fiber I used for that experiment with its loss coefficient, its length, its gamma value, and so this is the chromatic dispersion parameter. That's where you measure the dispersion in terms of wavelength instead of frequency as we do with beta 2. This is a tool online that you can use to convert this chromatic dispersion into a beta 2 value. And we also have an input and output loss here. Here we have the label on the laser source I used. This has 10 picosecond pulses and a peak power that goes up to 200 watts, but I don't think I actually used that in that experiment. I think it was more like 20 watt peak power, so let's use that below. Here's just a little picture of the laser I used. And here we see a snapshot from my video where you see the yellow trace here, that's the input trace that goes into the fiber in the spectral domain. And the purple trace that comes out, that's the output. So you can see that we definitely have a lot of broadening going on here. So let's see if we can actually get that same result out numerically. I note that the width of the yellow trace here is around 100 gigahertz, and the width of the purple trace is around 150. So that's like a ratio of 1.5. So keep that number in mind for later. Anyway, here we simply define the time base of the pulse as well as its the parameters of the fiber. And note here that we have to modify the duration a little bit, because since the negative 12 to 10 picoseconds, that's the sort of duration of the power part of the pulse. But of course, we want the duration to be in the amplitude domain, so we have to modify this by square root of 2. Okay, so we also can take into account the effect of input and output loss, as well as the attenuator used in the experiment, which was set to 16 for the picture taken above. So, defining the input pulse here and running the split step method, we can now take a look at the results down here. So if I plot it, let's see what we get. So going up here to the top, we see that the final pulse is actually compressed a little bit, and I think that happens because we have a negative value of beta 2 and a positive value of gamma. So it's some kind of like soliton, maybe shrinking going on here. That's another topic you might want to look into on your own. A bit beyond the scope of this presentation here, but it's not totally unexpected that the pulse will actually shrink in this case. Here we see the pulse evolution in 3D, and from above here, so actually you can see it sort of compresses a little bit, which is kind of interesting. And now we can also take a look at the spectrum, the initial one and the final one. So let's see, you have used the same color scheme here, and we get a certain spectral width here for the initial pulse going in, a certain spectral width for the purple one coming out here. And you can see we sort of get something that's kind of similar to the we saw in the optical spectrum analyzer. Now again, we can also see how it sort of evolves going through here. Again, if you look at the yellow and pink trace that we just numerically simulated, find that the initial trace here is around 40 gigahertz in width, and the final one, the purple one, is around 100 gigahertz in width. It's like a factor of like 2.5 between these, so that's a bit larger than what we got experimentally. But I think the reason is that in the experiment, you can see that this yellow pulse already has sort of 2 bumps. So I suspect it actually experienced a little bit of surface modulation inside the laser device before it actually got sent to the optical spectrum analyzer. So it's sort of modulated a little bit, and that's why it doesn't end up broadening as much as just a pure Gaussian pulse that we used in the simulation. But anyway, we get something that's sort of on the same scale, so that's pretty pleased with that. Alright, so I mentioned that we can use this split step method here, where we first compute the effect of dispersion and then surface modulation, and then we sort of loop over that. But of course, in a real realistic fiber, those two effects will actually take place simultaneously, and we're sort of artificially splitting that up into 2 different steps here. But of course, if we take small steps, we can sort of maybe, I guess, hope that the errors can be quite small. And it turns out that if we go through some theoretical considerations, then you'll find that the error should actually scale as delta z squared. So in other words, if you cut the size of the distance step in half, the error should become 4 times better, essentially. Let's actually prove that that's the case. So here we're going to follow the following strategy here. We're going to take the unit pulse that we got from earlier and use that as a baseline, because I think we used like 256 steps for that one. Then we're going to run the split step method multiple times, with first a single step, then 2 steps, and so on and so forth, until we reach the baseline, and then see how the discrepancy between the calculation with a small number of steps and the baseline actually changes over time. And then we can fit a model to that and see if it changes as alpha to the negative 2. So let us go ahead and run this, see what happens. So here we just have the baseline pulse, the list of number of steps, an empty error list. Then we simply loop here, find a new fiber every step we take, run the split step method, plot it and compute the error, see what happens here. We see that the actual baseline blue pulse is kind of hidden under all these other ones. But the idea is that if we only use a single step, then we get the orange pulse here, which is clearly very different from the baseline. Then for 2 steps, which is the green trace here, we get something that's a little bit closer to the blue pulse. Then for 4 steps, which is the red one here, we get something that's again a little bit closer. Keep going like this, we see that the computed result converges closer and closer to the expected baseline. Now if we make a plot of the sort of error between the blue pulse and the ones with fewer steps, we see that we get a model like so, if it's plotted in the double log domain here, with an a value of negative 2.1, so pretty close to negative 2 as predicted. Okay, so that's just a quick overview of this little notebook I wrote here to simulate the Nonlinear Schrödinger Equation using the split step method. So, as I mentioned before, there's a bunch of different upgrades you might want to implement here. You can also download it and just play around with it, try different pulses, see what happens. Something you might want to try out is to investigate how the runtime changes when you alter the value of n, so the number of time divisions. You may want to check out how the big O notation for the fast Fourier transform looks in order to maybe compare that. You can also implement what's called third order dispersion, which is a different phase term you have to use in the when solving the equation. It should be fairly straightforward to implement, actually. I think so. Another thing you can investigate is sort of how the chirp depends on the magnitude of beta 2. maybe how it depends on the magnitude of gamma. And also you can find, say, a negative value of beta 2 that will cancel out the chirp that's generated by gamma. That's another thing you might want to look into along with the concept of solitons. So anyway, I hope that was interesting and helpful. Don't forget to download the notebook, play around with it, and stay tuned for more videos. Bye bye.